can now describe the forces acting on each surface. We have that the force on the x surface, which is given by this vector here, df superscript x, is the combination of the three stresses on the x surface, sigma xx plus sigma yx plus sigma zx. Notice that this is a vector, so this x subscript here is not that this is the x component of a force. This is the total force on the x surface. And this has components on the x, the y, and the z direction given by the magnitude of the stresses on the surface x. Similarly, the force on the y surface, which is here, is given by the summation of the three vectors given by the stresses. Sigma xy in the x direction, sigma yy in the y direction, and sigma zy in the z direction. That gives you the vector df superscript y. And the force in the z direction, again, given by the combination of these three vectors. And putting it all together, the force on the cube is going to be given by the sum of these three red vectors, which we can write in component form, defining now indeed components of the vectors df subscript f, df subscript y, and df subscript z. Now these ones components in the x, the y, and the z direction. Now to have this description be equal to this description with the components df superscript x, y, and z given by the sum of the stresses, then we must have dfx here is the sum of the components that are multiplied by x hat. So that is sigma xx, sigma xy, and sigma xz. This is what is showing here. Df subscript y is the sum of the components that are multiplied by the y hat. So that's sigma yx, sigma yy, and sigma yz. Again, that's what is written in here in the middle line. And the f subscript z is the sum of the components that are multiplying z hat, which is given by sigma zx, sigma zy, and sigma zz, which is what is given here in the last line. Now you will notice that this has the form of a matrix equation. We can write this in the form of df is equal to sigma dotted with dA, where sigma is the following matrix. This will give you these three expressions when you do the matrix multiplication of sigma with dA. So the stress is a matrix where the columns, the first index, are the directions x, y, and z, and the rows, the second index, are the surfaces. So the surface x, the surface y, and the surface z. Now notice that the force is described as the inner product of the stress and the area. This is indeed how matrices behave mathematically. A matrix will transform a vector in both magnitude and direction. And this is an example of a rank 2 tensor. It needs two directional indices to describe it. Scalars are rank 0 tensor. They do not have any directional information. Vector is a magnitude and a direction. They can be expressed as an array once a coordinate system is chosen. And likewise, a rank 2 tensor can be expressed as a matrix when a coordinate system is chosen.